Alright, so that little exercise with the computer hopefully persuaded everyone that the frequency of the sound waves that come out when I strike the open string at 80 Hertz, and if I pinch the string halfway up, so the string is now half its original length, we've got a higher note, and the frequency was double, it was about 160 Hertz. And both of those notes are called E in traditional Western music, because that's what separates different notes, different octaves, which have the same name. They are all separated by being double the frequency of each other. So let's see how many notes E we could find on the guitar. Well, we started with the open string E, 80 Hertz, half the string, 160 Hertz, that's also E. And then we can go up the sort of do, re, mi scale, if you will, and find the next E, right? So there's the next E. So that must be double the frequency of this one. So 80, 160. Now what's 2 times that? It's 2 times 160, 320. So this must be 320 Hertz. And actually, that's the same note as the top E string. Sounds different, but it's the same note with the same frequency. We can halve that one again, and we can now go up to, what's that going to be, 640 Hertz. So that's the top E on the guitar. So we have 1, 2, 3, 4. There's 4 E's, right? And they're all separated by doubling the frequency. We get from one to the next. Now, why is that? Why is it that halving the length of the string, or halving the length of the string and changing the thickness of the string has this interesting effect? So we're going to look at what's actually making the sound. Right? We're going to pluck the string vibrates back and forth. Now another way of looking at it is say that a wave propagates back and forth up and down the string, and every time it does so, shakes the air and makes a sound wave come out. So a good place to start might be to ask, well, how fast does a wave propagate on a string? Now, I'm going to give you something that we're not going to derive. It's very tricky to derive. I'll tell you that the speed at which a wave travels along a stretched string is equal to the square root of the tension in that string, that's how tightly it is stretched, divided by m, the mass per unit length of the string, or how heavy the string is. So think of your different guitar strings, right? There's 6 of them, they're all about the same length, they're all under about the same tension, but they're very different masses, right? Some are heavier than others, and that accounts for the fact that they can strike with different notes. Now, what about that wave that travels up and down the string? Well, if we just make a very sort of simple diagram of the length of the guitar string held at each end, when it oscillates back and forth, it assumes a shape like this, and it quickly moves and assumes a shape like this, and it does it a certain number of times per second. A number of times per second is called the frequency. This is the length here, length of the string, L. Now this shape here is only half a wavelength, right? If I wanted to see a whole wave peak to peak, I could extend it out and come back to where I started. And in the meantime, my length that the wave has travelled is now 2L. Okay, that's the distance that the wave travels in one complete cycle. Now, of course, the string is only this long, so what actually happens is the wave comes across the string and bounces back and travels the whole distance that way. It still travels 2L. So that's how far it goes in one oscillation period. Now, how far something goes in a certain amount of time is another common name. It's the speed or the velocity. So we can write another equation for the velocity. Velocity or speed is always distance divided by time. Now, how far did that wave travel? Travel 2L. How long did it take? So 1 oscillation period, or 1 over the frequency, right? 1 over the frequency is the oscillation period. So just say 2L over P, or P is the oscillation period, which is the same thing as saying 2L times F. So now we've got 2 equations, here and here. And they're describing the same thing, the speed of the wave on the string. Now we don't actually care about the speed of the wave on the string. It's different for all the different strings. It's different for any guitar you pick up if the strings are made out of different materials. But what is not different for all different guitars is the notes you get. They all make the same notes, the same frequency. So we don't really care about V, but we have these 2 equations, so we can put them together and eliminate it, and in the process put together everything we know and everything we're interested in. So let's do that now. So I'm going to take the first equation, make it equal to the second equation, and then see what we get from there. So 2L times F equals the square root of T over M. I can rearrange my F, the subject formula, I'm sure you all can as well. change the sign, and 2 L's on the top and the left, you go to the bottom on the right. So, we have to put a cloud around it to show that it's an important equation. So we can see from the equation that if I stay on one string, all I can change is L, right, the length. I can't change the tension, can't change the mass of the string, but I can change the length. So if I halve L, I double F. If I reduce L by a factor of 3, so it's a third L, I get 3F, and so on up. So if I strike my string, get the fundamental, 80 Hertz. If I strike it halfway up, I should get double the frequency, 160 Hertz. If I go a third of the way up, this is a little tricky one. So what's 1/3 of the length of this string? It turns out to be right here. If I strike there, I should get 3 times the frequency. Oops, wrong one. I should get 3 times the frequency if I get the right string. Now, here's a good question. What if I go to 3 times the frequency and then double the length of the string? Right, so this is the third of the length of the whole string. So I could double it and it'd still be on the string. So if I could do that, let's go from there, up, brings me there, which is now 2/3 the length of the string, right? It's 2/3 of this whole thing, or it's a third times 2. Let's listen to that. Again, they sound the same note, even though they're not the same frequency. That interval, it turns out, is called a fifth, for reasons I never understood until very recently when I started learning the guitar, and here's why it is. If I go up the scale, starting with the open string, and I count the different notes, here's the first one, E, here's the next one up, F, G, A, B, and that's the fifth one, right? 1, 2, 3, 4, 5. So that's called the fifth. See, I never understood why it was called the fifth before, because it's a third the length of the string. Go figure. Let's see. I can't go to 4 times because I run out of room, but I can go to a quarter up here. That comes to right here. Right, there's a quarter of the length of the string. So there's a quarter, takes me to a half, takes me to 3/4, so just off the end of the fretboard takes me out down to the bottom. So that's a quarter of the length of the string. So I've got 3/4 of the original length here. If I strike that note, you would find that it had the same relationship. It's 3/4 of the length of the string. So the frequency will be 4/3 of the original frequency, right? So if I go half L, I get 2F. Third L gives me 3F. 3/4 L gives me 4/3 F. You see where this is going? 1/5 of L would give me 5F. So that argument goes all the way up the scale, and in fact that is how the scale that Western music actually uses was in fact developed. All the notes on the scale are very, very close to those relationships.